All right, so after tackling kinetic energy and the conservation of energy in our last sessions, we're now jumping into Chapter 9, Center of Mass and Linear Momentum. Now, have you ever stopped to think about what a car crash and a flowing river could possibly have in common? It sounds kind of weird, right? But believe it or not, the same exact fundamental law of physics is pulling the strings in both situations. We're talking about momentum.
And no, it's not a trick question. The answer to what connects the sudden, violent impact of a collision with the smooth, steady movement of water in a pipe is this one powerful concept: momentum. It's the secret language that all moving things speak.
So, to really get a handle on this universal law, let's start somewhere familiar. Let's talk about the world of solid objects, things actually smacking into each other.
At the heart of it all is this idea of linear momentum. The easiest way to wrap your head around it is to just think of it as mass in motion. It's basically a measure of how much oomph a moving object has. So picture a bowling ball and a tennis ball rolling at the exact same speed. Which one is harder to stop? The bowling ball, right? That's because it has way more mass and therefore way more momentum. This concept is the key to figuring out what happens when forces act over time, like during any kind of impact.
Now here's the golden rule, the most important law of the land when it comes to collisions: the law of conservation of linear momentum. All it says is that in a closed system, which is just a fancy way of saying a situation where no outside forces are interfering, momentum can't just appear or disappear. It's simply passed from one object to another. Whatever you start with, you have to end with. It's one of nature's strictest accounting laws.
And using this law is actually pretty straightforward. It's a simple two-step dance. First, you add up the momentum of every single object in the system right before they smash into each other. Got that number? Good, because that total amount has to be exactly the same as the total momentum of everything right after they've collided. It's an incredibly powerful tool that lets us predict what's going to happen.
So let's put some numbers on it. Let's say we have a couple of objects moving towards each other, and their total combined momentum before they collide is 36 kilogram-meters per second. Then they crash and stick together, forming one new object that has a mass of 5 kilograms. Using our conservation law, we can figure out exactly how fast that new blob is moving. It's got to be 7.2 meters per second. The math just has to balance out.
And what's cool is that this rule applies to all kinds of collisions. You have your completely inelastic ones. Think of a car crash, where the vehicles crumple and become one tangled mess. In that case, momentum is conserved, but a lot of the kinetic energy, the energy of motion, gets lost as heat and sound. But then you have elastic collisions, like a perfect break in a game of pool. The balls click off each other beautifully. In that case, both momentum and kinetic energy are conserved.
Okay, so we've got a good grip on how momentum works for solid objects. But what about things that aren't so solid? What happens with liquids and gases?
Yeah, this is where things get really interesting. We're shifting from the world of sudden impacts to the smooth, continuous world of fluids. How does something like momentum get transferred in a river or through the air?
Well, the secret ingredient here is something called viscosity. Honestly, the best way to think about viscosity is just as a fluid's internal friction. It's what makes honey thick and gooey and water thin and runny. And it's this very property that allows momentum to be passed along from one layer of fluid to the next.
Now, here's a mind bender for you. It's called the no-slip condition. And it means that the very, very thin layer of any fluid that's directly touching a solid surface isn't moving at all. Its velocity is zero. Think about the dust on a ceiling fan. You turn that fan on full blast, and the blades are whipping around. But the layer of air and dust right on the surface of the blade is actually stuck to it, not moving relative to the blade at all. Wild, right? So that no-slip condition creates this super thin region called a boundary layer. Imagine the water flowing in a pipe is like a giant deck of cards. The card at the very bottom, the one touching the pipe wall, is stuck completely still. The card just above it gets dragged along a little bit by the layer above it, and that layer gets dragged by the one above that, and so on, until you get to the cards in the middle of the pipe that are moving at full speed. Momentum is being transferred, layer by sticky layer, from the fast-moving center all the way down to the wall.
Okay, so we have collisions on one side, and we have flowing water on the other. How on earth do these two worlds connect? Well, it turns out that a car crash and the flow of water in a pipe aren't just neat analogies for each other. They are literally two different expressions of the same, single, fundamental law of physics.
And this slide says it all. Now, hey, don't get hung up on the crazy-looking equation on the right. Just focus on the big idea here. On the left, you've got a pretty simple equation for a collision. On the right, a much more complex one for fluid flow.
They might look like they're written in different languages, but they are telling the exact same story. A story about how momentum is transferred and conserved within a system.
So what's the big takeaway? It's that momentum gives us this incredible, unified way to understand motion in systems that on the surface look like they have nothing to do with each other. It's the master key.
So let's wrap this up. Momentum is one of those things that is always conserved in a closed system, period. In the world of solids, that momentum gets transferred in big chunks through direct impacts. In the world of fluids, it's transferred smoothly and continuously, thanks to viscosity. This one idea connects everything, and it's absolutely critical for engineering pretty much anything that moves, from designing more efficient pipelines, to building the wings on an airplane, to calculating the thrust of a rocket.
You see, the transfer of momentum isn't just some abstract idea in a physics book. It is the invisible hand that shapes our world, from the way a raindrop splashes to how a supersonic jet is designed. Understanding it gives us the power to describe, predict, and engineer the world around us. So now that you can see this fundamental force at play everywhere, what will you build with it?